Okay, so sorry about last week. I forgot to press the record button. Hopefully the quiz went okay. This week your quiz is going to be on inductors and maybe an RLC circuit in series according to Zorman. Um, so I'll just get started. So inductors are they're like the opposite of capacitors in many ways, but in other ways they're like very similar, especially in terms of how you're going to be like approaching the problems. So an inductor, the key thing for an inductor is that let me get the equation. Inductor uh, voltage. Yes, the inductor voltage is equal to L times di dt. And if you remember for a capacitor, it was that the current is, wait, did I get this backwards? No, I don't think I did. The current is C times dV dt. You kind of swap those around and you get the capacitor one. So what this tells you is that the inductor is going to work in much the same way as the capacitor, but with voltage and current swapped. So what that means is that where you can think of a capacitor as like a battery that charges up and discharges, a inductor is like a current source that charges up and discharges. So the key thing there is that the inductor will resist changes in current, whereas the capacitor resists changes in voltage. So what does that look like in practice? So just like how for the capacitors, you would find an initial voltage and then a final voltage. For an inductor, we want to find a V of 0, which is, or not a V, sorry. This is exactly what I'm saying. Yeah. So for here, we want to find an I of 0 minus, which is going to be the same as our I after some kind of switch closes. And then we also want to find an I of infinity, which will be the current far in the future. And then very similarly, our equation will be like exactly the same, where it's I of infinity plus, I might be getting this wrong right now, but if I get it wrong, I will fix it later. I just do not have the thing right in front of me. Let me make sure I'm doing this right. Uh, yes, that's right. Okay, e to the negative t over tau, and in this case, tau is L over R. Remember, for capacitors, it was R times C, now it's L over R. So that's that. I will do example problems. Hopefully you all know how to do capacitor problems right now, and you will find that inductor problems are very similar. So I'm not really going to go into any more of that for now until we just get to practice problems. But basically, opposite of capacitor. No, not really opposite. I'll say capacitor, but for current, because that's really what it is. Capacitor, but for current. So then the other thing that's probably going to be on your quiz is RLC circuits. So that means we have a resistor, an inductor, and a capacitor. So in this case, that means that your final circuit, so with an inductor, right, when you're finding this, the goal is to get a circuit that looks like the inductor in series with a resistor, and then that would be your R and your L. Whereas with RLC circuits, your quiz, according to Zorman, he said you may. I don't really know if that means you will or you won't. I'm assuming it means you probably will. But he said you may have a question with a series RLC circuit. So what that means is your final circuit is going to look something like this, where you have a capacitor, an inductor, and a resistor. Crazy, I know. And what you will be provided with is a chart that looks a little like this. Let me copy this over. And so you can solve these kind of circuits manually. It takes some like differential equations. But what we have here is basically just the solutions of all those differential equations for you. So I believe on your quiz, you will be provided this exact chart, but it will be missing this top section. So you'll have to know which side is parallel and which side is parallel and which side is series. So on the left here we have series, and on the right we have parallel. And the reason an easy way to figure this out is the two options here. So we have parallel and we have series, right? If they were in parallel, then it would look something like this. And if they were in parallel, then the voltage across all three would be the same because they're connected on all sides. So it would not make sense to have your variable that you're looking at be voltage. So basically, you're going to be looking at basically these equations either give you it lets you find some variable in the circuit, and then from that you can find the rest of the variables through like Kirchhoff's voltage law or like the equations for like the derivative equation like this and so on and so forth. But basically, if you're dealing with a voltage, it's probably series. If you're dealing with a current, it's going to be parallel. So for now, we are going to look at this half. Another thing is that on your quiz, these will not be given to you. These sections that tell you which equation is which. So you just kind of have to remember those. Remember those however you want. It's just 3 sections of a table. Hopefully you can come up with some kind of mnemonic. I don't know. If A is big, then it's the top one. If alpha is big, it's the top one. If alpha is small, it's the bottom one. So what are these alpha and omega? So alpha, if you look here, is basically it's essentially your time constant for I think that's kind of accurate. It's basically your time constant for this case. It's different for series and parallel. And for series, it is this value, R over 2L. And basically what you're going to do here is you're going to find this alpha and you're going to find this omega based on your final circuit. You're going to find those two numbers and you're going to say, okay, is it bigger, is it equal to, or is it smaller? And then based on that, you're going to use one of these sets of equations. I will go through an example, but there's not really much I can explain here besides simplify your circuit to this form, figure out what your RL and C values are, and then find this alpha, find this omega, and then from there, compare them, and then use the proper set of equations based on that. So with that, you also will need to find your VC of infinity, your VC of 0, and yeah, but that's kind of all you need to do. It's very like systematic. You just kind of go through and do what it tells you to do. There's also these intermediary variables like S1 and S2. Those are also found here. So it's really just make sure you bring your calculator. If you don't have your calculator, you're kind of screwed. But it's really just going to be like plugging stuff in. I'm just going to start doing example problems now. If anyone has any questions as I'm going, ask in the chat or speak up, and hopefully I will notice. So to start, I will do a inductor problem. Let me decide which one I want to do. Okay, yeah, this one's very straightforward. I will do this one first. So 9 volts, 30 ohms, and then we have our switch here, and it goes like that, and we got that, and that. Okay, 30 ohms, 150 ohms, 60 ohms, 0.2 henries plus minus. Okay, so here the goal is to find VL of t. And at t equals 0, the switch moves. So the same way we did with capacitors, we're going to do this by analyzing the circuit before the switch moves and then after the switch moves. So for t is less than or is less than 0, right? The switch is down. So we ignore this part of the circuit and we redraw the circuit as such. So here, I could fill in all the values. I'll fill in all the values, I guess. But remember, what we're trying to find for an inductor, for just an inductor question, is we want to find this equation, right? I will copy this over, actually. Oh, wait, one very crucial thing I did not talk about with the inductors. So an inductor, just like how it is the opposite of a capacitor in many ways, um, it's also the opposite in terms of steady state behavior. So at steady state, an inductor is the same as a wire. So how you can think about that is at steady state, the current will have stopped changing, so the voltage drop across it will be zero, and the voltage drop across a wire is zero. Um, and at a step response, it's going to be equal to a current source with the value of IL of 0 minus. So we'll see that in a sec. So here, if you look at this circuit though, right, if this is your steady state circuit, there's no power source, there's not going to be any current flowing in the circuit. So you can very easily just say IL of 0 minus equals IL of 0 equals 0 amps. So that's just an easy way to get started. So then for t is greater than or equal, or is, I'll say equal to 0. Actually, no, greater than or equal to 0. The switch moves and the rest of our circuit gets introduced. Okay, we got our 0.2 Henrys, our 60 ohms, our 150 ohms, and our 200 ohms. That was 30. I don't know how I read 200 there. 30 ohms and 9 volts. So now what we want to find is we want to find the current as time goes to infinity. Oh God, my Apple battery. Oh, that's actually really bad. The current as time goes to infinity, and we also want to find our L over R. So where do we get started? Here. So what we're going to do is it'll be easier to find that time going to infinity current if we can simplify the circuit to just like one resistor and just the inductor. So we'll start by wanting to simplify the circuit. I look at this, I say, I want to simplify this. I don't know where to start. The easiest way to start is just start by combining things that are next to each other. So we got 9 volts, and then this would become 180 volts, or 180 ohms, 60, and that. So this is 180, and next to a 60, and then that, we can then do a source transform. Which will become, this will stay a 60 because this has not changed, and this will stay a 180 because it has not changed. And the current will now be 180 over 9, which is, or other way around, sorry, 9 over 180, which is 0.05 amps. And then there's 180 in parallel with 60, so that's going to be 180 times 60 over 180 plus 60. Trust me on this math, it is going to be a 45 ohms. So this will go to something that looks a little bit like this. 45 ohms. And then from here, we can think about how our circuit will behave. So this circuit is equivalent to this circuit, right? I'm gonna get out my Apple Pencil charger. I might have to take a small, like 5-minute break later to let this charge up. Hopefully I will not. Maybe it'll all just be good and this will last an hour on 5% somehow, but either way, we don't know. So let's start with the time going to infinity. So as time goes to infinity, remember, the steady state condition for a inductor is that it becomes a wire. So if we have this circuit and this becomes a wire, then what will happen is at steady state, all the current will just flow through the wire because a wire has no resistance. It'll preferentially flow through there. So what that means is that our IL of infinity equals 0.05 amps. And then we also need to find our tau, and our tau is L over R. And just like with a capacitor, or yeah, just like with a capacitor, you want to neutralize the source when you're finding that L over R. Doesn't really matter how you think about it, or you can just like ignore the source. But here it's just going to be that 0.2 over 45, and that gives us 0.0044 for repeating seconds. It has a unit. It doesn't really matter what the unit is. And then from there, you can just kind of write your final equation. We got, or not, we're actually not quite there yet. Sorry, because remember, we're finding VL of t, and we're finding the equation for IL of t right now. So I am kind of out of space here. Let me just kind of shrink everything I did. Okay. So we're here. We found IL of infinity, we find IL of 0, and we found our tau. So now we can write IL of t equals that IL of infinity, 0.05, plus, do I still have this copied? That'd be crazy. Ooh, I do. Okay. Plus our 0, plus our 0 minus 0.05 e to the negative t over 0.0044. And from there, you can simplify this a little bit, and you get 0.05 minus 0.05 e to the negative 255. That feels right. That could be right. Yeah. Negative 200 and, oh no, not 255, 225 t. Let me double check that. So that would be 4 over 0.2. No. Oh no, that's not 4s, that's a 45. Okay, yeah. Yeah, so 45 over 0.2, yeah, 225. And this would be amps. However, we want to find our voltage. And so we go back to our fun equation. That voltage is the inductance times di dt. So that means VL of t is going to be L, which is 0.2, times the derivative of this. So actually, I'll just write this out real quick. L di dt equals 0.2. The derivative of this is going to be negative 220. This is a constant. This disappears. So then it's negative 225 times negative 0.05, which is going to be 11.25, I believe. Yeah. So it's going to be 0.2 times 11.25 e to the negative 225t, which is equal to 0.2 times that. So times 0.2 is 2.25 e to the negative 225t volts for time is greater than or equal to 0. And that would be your final answer for this question. So again, it's very similar to the capacitor questions. You're just kind of finding the opposite values. It's like, it's very similar, but you're doing the opposite things. Now I will move on to the next question. I'm gonna plug in my Apple Pencil for like 10 seconds here while I move to the next question. Okay. I'll do like one more inductor question, and then I will do an RLC question, I think. Yeah, this one looks good. I will do this question. How's my Apple Pencil looking? That's pretty low, but it'll be okay. I'll just do it quickly every so often. Okay. So next question, another inductor question, a bit more complicated, but hopefully not too bad. Again, this is the kind of thing that like would be expected of you to be able to do on a quiz. So Okay, so what this is saying is that the switch was closed, and then at 0 seconds, it moves out of the way. So again, the way that we're going to approach this is we're going to say, okay, for time is less than 0, we analyze the circuit to find our initial current. So I will redraw this real quick. This time it's pretty simple to redraw it. You don't actually need to redraw it if you can just kind of think about it in your head, but it can help to help you not make mistakes. So we want to find that IL of 0 minus, which is whatever this current will be, assuming this is a wire. Because remember, we're in like steady state here. We want to find this current. So there's many ways you can do this. You can do it kind of however you want. I look at this and I think, there's quite a few ways you could do it. Yeah, let's do mesh current, I think, because mesh current is pretty chill in this kind of scenario. So we got mesh current, mesh current. This can be I1, I2. You could equivalently do this with node voltage, but I know a lot of people prefer mesh current, so I'm going to do that. So here we're going to see that we actually don't know which way this is going, but I'll say that the current through this capacitor is going to be equal to that I2 once we solve for I2. So for I1, right, we're going to have minus 12 plus 2 I2 plus everything here too, yeah, plus 2 oh, not I2, sorry. This isn't I1 plus 2 I1 minus I2 minus, or no, here it's a plus actually. Wait, no, it's another minus. Minus 4 equals 0. And we can simplify this a fair amount. I will simplify this to eliminate I1, I think. So this will be move everything to the side. 16 equals 2I1 plus 2I1 minus 2I2. And then we want to eliminate I1. So this is 4I1 equals 2I2 plus 16. So then I'll leave that there and see if it works nicely with the next one. So then for the next equation, we have very similar stuff. I'm going to start here. So we have 4 volts plus 2I2 minus I1. And then here, this is just a wire because we're at the steady state condition. After a long time, the current is not changing anymore. And since this is the equation for the voltage, if there's no change in current, there's no voltage. So plus 2, and then plus 2 times I2 equals 0. So here we have that it'll become, if I want to find I2 at the end, what this is going to be, I'm going to do a bit of simplification just kind of fast here. 4I2 equals 2I1 minus 4. I think I did that right. Surely. Yeah, that looks right. So then if I want to find 2I1, I'll divide this by 2. So 2I1 equals I2 plus 8. So then we have 4I2 equals I2 plus 8 minus 4. We subtract I2 and we combine the constants. We get 3I2 equals 4. And then I2 equals 4/3 amps. And that is going, we have determined, to the right. I'll say to the right, because that'll determine the positive or negativeness later on. So then that also equals our IL of 0 minus. So now we want to analyze the circuit after the switch has been flipped, after the switch has been flipped. So in that case, what's going to happen is we're going to have the circuit again. But now, since this is open, there's no current going through that middle section, and we can ignore all of it. So now our circuit is pretty clean and straightforward, just like so. So as time goes to infinity, right, this is going to be a that's going to be a wire, right? So what we will see is that the circuit can be rewritten as our 12 volts. And then you can combine those two resistors because they're in series. Even though they're on opposite sides of the inductor, they're still in series, so it counts to H. And this would be your circuit, simplified a little bit. And remember, when we're finding the when we're finding the tau, we want to neutralize the sources. So in this case, you neutralize this source you neutralize a voltage source by turning it into a wire, because the wire has 0 volts across it, which is like the opposite of having a voltage source. So here, again, the two things we're finding, let me put that other equation up here, because this, remember, always keep your goal in mind. This is your goal. We have our I0, and now we want to find our I infinity. So for I infinity, that'll be the current through this circuit when this is a wire, right? So when that's a wire, this current, so we can say IL of infinity is very simply just 12 volts over 4 ohms, which is 3 amps. Units are good. And then our tau is going to be 2 over 4, which is 1/2. And now we have all the parts to make our final thing, which is going to be IL of t. Let me write this a bit higher, actually. IL of t equals IL of infinity. Remember what's up there? IL of infinity, so 4/3 plus, we got, oh wait, no, I wrote this wrong. Oopsies. Because infinity is 3. So 3 plus 4/3 minus 3 e to the negative t over 0.5, because it's 1/2, which we can simplify a bit to 3 plus 4/3 minus 3 is 4 minus 9, which is negative 5/3. So this is negative 5/3 e to the negative 2t amps for t is greater than or equal to 0 seconds. If we were then also asked to find the, okay, let's say, for the sake of argument, we were asked to find this current, or this voltage, right? This is actually what's on the question that I'm looking at. But let's say we were told to find this VO as well. So here we have to look at the circuit and say, okay, what's the current going to, or what's the voltage going to be over time after the switch has been opened for that resistor? So the key thing here, remember, for a resistor, V is simply IR, right? And there's only one loop in this circuit. So if we found IL of t, that's going to be equal to, the current for everyone. So if we want to find that voltage, right, it's just going to be 2 times that thing we got. Because V equals IR, I equals, I'll write this as a better form here. So V out, or VO of t, is going to be equal to IO of t times R, which is equal to IL of t times R, which is then going to be equal to that expression from before. So 3 minus 5 over 3 e to the negative 2t amps times 2 ohms, which gives us our final answer of VO of t equals 6 minus 10/3 e to the negative 2t volts for t is greater than or equal to 0. So hopefully you can see there, once you find a current or a voltage, you just kind of treat that as a variable and then go back to your circuit and say, okay, I know the current through here, So what does that tell me about the rest of the circuit? And in this case, what it tells you is that the current through here is the same thing because it's one loop. And from there, you can find that voltage. And that's pretty nice and straightforward. Okay, I think I will stop there for inductors, and now I will try to tackle an RLC circuit. These just take a long time. There's no easy way to do them. They're a pain in the ass, but you know, that's what the class you're in is about. So that's what you're doing. So let me find the one I was going to do. Again, you're going to have an RLC series circuit. So let me make sure I actually am doing a series one here. Okay, yeah, this question works. Yeah. Okay, so here we got power source, 10 volts, 4 ohms, and then a switch that will open at time equals 0. And then the rest of our circuit is a 0.02 farads, a 3 ohm resistor, a 6 ohm, and a 0.5 Henry. Okay, so much in the same way as we handled the inductors and the capacitors, we're going to start by looking before the switch has moved and then after the switch has moved. So before the switch has moved, the circuit looks a little something like this. This is a 10. This is a wire. And then I'll actually fill in like the models for the capacitor and the inductor here. So the capacitor is a wire, or the capacitor is an open circuit. So this is T less than 0. And this is a wire. Hopefully you are all familiar with that by now. And this is connected because the thing is closed. And so what we want to find here is, since if we look at this, right, if we look at this circuit, after this switch is opened, then all we're left with is, oh, I have a laser pointer. Once this opens, all we're left with is this part of the circuit, which is going to be a series RLC circuit. So with that, we want to look at our table and say, okay, for a series RLC circuit, what kind of variables do we need? And for the variables that we need this VC of infinity and the VC of 0 and an IC of 0, actually. So we'll need to find all 3 of those. Yeah, and that seems to be all we really need. So we'll look at that. So here, you can actually ignore this section because this resistor doesn't matter in this case. And if we want to find that VC of 0, that's going to be from here to here, which is going to be the same as from here to here, because this is a wire. It has no relevance, you know, it doesn't have a voltage drop across it. So what this is simply is that VC of 0 is going to be equal to the V of that 6 ohm, which is going to be our 10 volts times 6 over 4 plus 6, which is 6 volts, right? And then similarly, we want to find the IL of 0. You know, that's the other thing we want. The IC of 0, the VC of 0, and the VC of infinity. So the IL of 0 is going to be whatever the current through this wire is. And in that case, it's just the general current of the circuit, because here we only have one loop. Yeah. So it's going to be 10 over 4 plus 6, which is simply 1 amp. Okay, now we found our values for the initial state of the circuit. Now we want to find our values for after the switch moves. And for this, I will just copy this part. That didn't quite work how I hoped it would, but okay. So this becomes our circuit now. And one nice thing is that you can combine these two resistors immediately. So I'll actually do that here. Because since they're in series, you can just kind of do this. It works fine. And what we see, actually, you can like kind of do it. I'll not do it because we know the voltage across here, and it won't be accurate if I move those resistors together. So this is 6 volts, and this is going to be 1 amp at time equals 0, of course. So again, how we're starting this is we look at this chart. We say, okay, we need to figure out which one of these 3 sections am I using. So we want to find our A, we want to find our alpha and our omega. So alpha for a series is R over 2L. Which is going to be that 6 plus 3, so 9 over 2 times 0.5, which is simply going to be 9. And it has a unit of 1 over a second, but you don't have to care about that. And then omega naught is 1 over the square root of LC, which is 1 over the square root of 0.02 times 0.5, which is going to be equal to 1 over the square root of 0.01, which is 1 over the square root of 0.1, which is 10. And that also has a unit of per second, but again, you do not need to care about that. They are just numbers for the sake of this course. So yeah, we're here, we have W naught, and we have alpha. And what we do is we look at, okay, how does alpha compare to omega naught? So here we see that our alpha is 9 and our omega naught is 10. So alpha is very clearly less than omega naught. And that means we are using this 3rd section. And not that it particularly matters right now, but a nice little intuition about these 3 different regions is if any of you guys have taken like differential equations or anything of that sort, you might not have. I don't think it's required for this class, but what you have is there's 3 kind of responses a system can have. It can either be overdamped, critically damped, or underdamped. The idea is that when something is overdamped, it like returns to its resting state kind of slowly. If it's critically damped, it returns to its resting state as fast as possible. And if it is underdamped, it'll like wiggle back down. So basically, if your resistance is too small, then it'll wiggle. If your resistance is just right, it'll be critically damped. And if its resistance is too big, then it'll be overdamped. That's like something you can think about. You don't really need to think about it. That's just some math that you'll learn eventually if you're an engineer. So moving on, that means this here is our section. So I will copy this screenshot over to the other page actually, because I would like to be able to look at it. So here, I think I can crop this freehand. It said crop, freehand crop. How does this work? I just, we had A is less than omega, so no. Done. Ooh, that looks disgusting, but it works. Okay, so A is less than omega, and we're using these equations. So I'll start by calculating that omega d, which is going to be the like value inside of the sine and cosine. So omega d equals the square root of omega naught squared. So I'll just fill in those values. So omega naught squared is 10 squared minus 9 squared, which is going to be a square root of 100 minus 81, right? But square root of 10 squared minus 9 squared is going to be 4.36. And then we also want to find our D1 and our D2. D1 is simply VC of 0 minus VC of infinity, which for us, as we found earlier, VC of 0 is 6, and our VC of infinity is going, so it could be if your circuit has a power source in it, that your VC of infinity could be an actual number. In our case, similarly to how if you have just a simple LR circuit or an LC or a RC circuit, so if you just have a capacitor and an inductor and a if you just have a capacitor and a resistor, or you have an inductor and a resistor, the energy is going to all be dissipated through the resistor eventually. There's nothing like adding energy back into the system. So here, our VC of infinity is going to be 0. I should have written that earlier. But here you can see, since no source, VC of infinity is 0. So that our D1 is just going to be 6. And then our D2, that's the kind of scary looking one. We have that 1 over C IC of 0. So 1 over C, our C is 0.02, so that's 50. 1 over 0.02, I'll just write it as 0.02. IC of 0 is times 1. And then plus alpha is 9 times our what is basically our D1. So times 6 over omega D, which was 4.36. And that will get us, what is this? 50 plus 36 over 4.36, which is, let me make sure I do this right. Why is this different? Oh, okay. The key thing here is that this is something you should consider when you're doing this, actually, is that since we have a positive 6 volts and we defined it like that, then our current here has to have a sign that agrees with that. So if we have a positive 6 volts there, that means that if we have a current going like that, then this would actually be a negative 6 volts. So what we have to do instead is say that this is a negative 1 amp, because then it matches up properly. Let me see if I can get you a slightly better explanation than that. Give me a sec. Um, doo -doo -doo. No, there's not really a better explanation than that, but oh wait, no, here's a better explanation than that. Okay. Yes, since it says this is actually IC of 0, you see it's a C. I kind of misspoke earlier when I said we were finding IL of 0. The reason it's useful to find IL of 0 is because here IL of 0 is going to kind of equal IC of 0, right? So what we find though is that if we have our IL of 0 going that way, right, then our IC of 0 will be going the other way, I think. I'm just looking at the notes I have from a previous year, and I'm not sure I fully agree with them. Give me a sec. Because it's either a -1 or a 1 for that current, and I'm not exactly sure which. Could be, yeah, I see 0 equals -0. Hmm, is that right? As for the drawing above, I see 0 equals -0. Sorry. Now let me charge my Apple Pencil while I am contemplating this. Um, Okay, I'm just gonna go with what it says here, that IC of 0 is actually going to be a negative number or a -1. So this becomes a negative. I sadly do not have an actual reason for that. I can look at the notes in like a minute, but this is where it gets tricky, you know? There's a lot of variables and you have to kind of put them in the right place. I don't really have a good explanation here. But this becomes a -1. What's written here is that IC of 0 equals negative IL of 0, which would be -1. I'm not exactly sure why. I'll keep thinking about it as I write this. But then we get -50 plus 36. No, that's 54, not 36. I don't know. I thought it was that. Over 4.36, which equals a 0.917. And then our final answer, we just fill in all those variables to here. So our final answer would be VC of t equals a e to the negative alpha, so -9t times d1, 6 cosine that omega d, so 4.36t plus d2, 0.917 sine omega d, which is 4.36t, and then plus VC of infinity. And VC of infinity, as we found earlier, is just 0. So this would be our final answer, VT greater than or equal to 0. Yeah, so it's a lot of work. The bulk of it, though, is just like this end section. You just got to plug in a bunch of stuff into your calculator. Make sure you don't plug it in wrong to your calculator. That'd be annoying. Yeah. I don't know if I have time to do a whole another question of this sort. But let me look to see if I have any other good ones to do. And if anyone has any questions, now would be a good time to ask. Anyone in chat or anyone want to speak up, feel free. Okay, in that case, since no one seems to have any questions, I think I will call it there for the day. Good luck if there is actually a RLC question. I think there probably will be, just judging from the announcement that Zoran put out. Uh, Make sure you look at this table nice and closely. Make sure you know which is overdamped, which is critically damped, and which is underdamped, which section corresponds to which alpha and omega, because that will be like blotted out on your exam. He posted in the announcement what the sheet is that you will be getting. So look at that, familiarize yourself with that in advance, so on and so forth. Other than that, yeah, that's kind of it. Inductors are like the same as capacitors, but they have the opposite steady state behavior and they deal with currents. And RLC circuits are when you have all three of them and it does funky stuff and it's annoying. But yeah, that's all for today. I will end the recording now.